Hey everyone, welcome to our last unit of the semester. It's a unit on systems. So look in a new folder for the new material because we're starting systems. And this is going to be assignment 77. Assignment 77 in systems is all about solving two variable systems. Um, you know, we've been solving systems since Algebra 1, and I'm not quite sure that this is going to be any particularly different than that. It's just bringing it to the front of your memory. So how about for bell work, we do a couple of problems just to see where you are and what you've got, okay? 3x plus 2y equals 12, and x plus y equals 4. Will you solve that system? Now, I don't particularly care what method you use. I believe our textbook is using primarily substitution here. But if you're more comfortable with another method where you can show some work, that's fine with me. Okay. So go off and try this one. Come back when you're ready to talk about it. Hey everyone. So this one, I think I'm going to do it with substitution. And I'm going to say that y is equal to 4 minus x. So you solve one equation, doesn't matter which, for one of the variables. Then plug this into the other equation. So we picked one of the equations to solve for one of the variables. I went with the second equation so I wouldn't have any fractions to deal with. And then once you've solved for either variable, you take this and plug it back in. So I don't want to plug it in for x because it doesn't say x equals, it says y equals. So I'm going to plug this stuff into that y. Okay, so first step, second step, let's go. 3x plus 2 times 4 minus x equals 12. We'll distribute here. Don't forget to distribute there. A lot of people do. It's kind of sad. X plus 8 equals 12. And if I subtract 8 from both sides, I get x equals 4. But remember, a solution to a system of equations is really a point of intersection between these two functions. So having an x coordinate is good, but I'm not done yet. My answer is a point of intersection. So I still need a y value. I can certainly take this x equals 4 and plug here or plug here, but come on, it's already called y equals. It's exactly the thing I'm looking for. So 4 minus 4, then y equals 0. Please don't list your answer like that. I would really like you to show me that you recognize that the solution to this system is a point on a graph. It's a point of intersection. It's the solution to when these two equations are equal to each other. So that was substitution. And I believe, substitution is something that many people were very comfortable with. It works in lots more situations than elimination does. So there's value in reviewing substitution. But I know that many of you wanted to do this with substitution. So for those of you, I'm going to multiply this by 3. My top equation stays the same. But the bottom equation is now 3x plus 3y equals 12, right? 3 times 4. And I subtract. Now, if these coefficients have the same sign, I subtract. If they have opposite signs, well, I want to add them. I want to use whatever adding or subtracting here makes sense to eliminate one of the variables. And for this problem, where the coefficients are the same, I'm going to subtract. So 3x minus 3x, they cancel. 2y minus 3y is negative y. And 12 minus 12 is 0. So if I divide both sides by negative 1, I get y equals 0. And that's cool, because we found that with substitution. But I still need the other variable's value. What is that ordered pair at the point of intersection? So I can take this y equals 0 and plug it in here, or here, or here, or here. It doesn't matter where I plug it in. I'm going to plug it in up here. 3x plus 2 times 0 equals 12. Not equals, but does equal 12. So this becomes 0, and so I have 3x equals 12, or x equals 4. Yay! So I also get 4 and 0, but again, don't list your answer as x equals this and y equals this. Please give me your answer as an ordered pair. Otherwise, I'll mark it not sufficient. Not because it's wrong, but because it's not what I'm asking for. All right, so there's one. How about this one? 3x plus 2y equals 12. And y equals negative 3/2 x. Will you please solve that system? Okay, so it's already set up for substitution. I know what y is equal to, so I'm just going to take this and plug in there. 3x plus 2 times negative 3/2 x equals 12. Well, these cancel. And then I have 3x minus 3x equals 12, and 0 equals 12. What's that mean? Well, these numbers are not, in fact, equal to each other, and so what this means is there's no solution. And since these are linear equations, what we know is these lines have the same slope, but not they have the same slope. They're parallel lines. Parallel lines will never intersect in the Euclidean universe. In non-Euclidean geometry, parallel lines can actually intersect, and triangles can have more than 180 degrees. It's a very interesting place, but right now we're working in the Euclidean universe where parallel lines don't intersect. And since a solution to a system is a point of intersection, we know this has no solution. Okay? And then what about this one? Also with 3x plus 2y equals 12, but now I've got y equals negative 3/2 x plus 6. Will you solve this system, please? Okay, so I would really like to, I really want to be a little more specific this year than you were before. So what I mean is, when I take this and substitute in there, I'm going to have 3x plus 2 times minus 3/2 x plus 6 equals 12. So I distribute. These will cancel, leaving me minus 3x plus 12. Here I have that plus 3x and equals 12. Well, these cancel, and 12 does equal 12. And in the past, when we saw something like 12 equals 12, we would say something like, well, there's an infinite number of solutions. And that's okay for little guys, but you're a big person now, and knowing that there's an infinite number of solutions, great, but I also know there's an infinite number of things that aren't solutions. So how does that help me? It doesn't help me at all. What I want instead is to build a little machine that when you plug a number into it, will generate one of the solutions. Yeah, an infinite solution machine generator. Yeah, so what's that going to look like for us? Well, whenever we have the case of infinite solutions, whenever you're tempted to write infinite solutions, first, don't. And second, this is what you need to do. You need to take y, I'm sorry, you need to say, okay, whenever I have infinite solutions, I'm going to say x equals a. No, it has to be x and it has to be a. Why? For the same reason we drive on the side of the road that we do in this country, but some people in other countries don't. Because a long time ago, it was decided that that's what we're all going to do, and so we all do that. Now that you know what x is, go into one of the equations, and it doesn't matter if you use this one or this one, x plus 6. I myself would use this because if I'm looking to build an ordered pair, because my solutions are ordered pairs here, then I want an x value and a y value. And this one's conveniently already solved for y, so I'm going to use this, and I'm going to take what x equals and plug it in there. So I'm going to have y equals negative 3/2 a plus 6. Now, what's this all about? Well, my ordered pair then is a, comma, negative 3/2 a plus 6. This is a little machine that will generate ordered pairs when I plug any number in for a. If I plug a 0 in for a, 0, 6 is an answer. If I plug a 2 in for a, the 2's cancel, negative 3 plus 6 is 3. 2, 3 is going to be a solution. I could plug in negative numbers, I could plug in decimal numbers. This type of solution is called a parametric solution. And it's called a parametric solution because we're using a parameter, i.e., we're using another variable. We're rewriting this stuff that was originally in x's and y's in terms of a new variable. Here, we're using x equals a. And for all two-variable systems, whenever you need to do a parametric solution, you're going to set x equal to a. That's our agreement, okay? So, parametric. Solution generating machine. That's what we want. Now, some people don't see to use that y equals negative 3/2 x plus 6 equation. They want to use this equation. So for the people who do that, or if you were given two functions that look like this, simply plug x equals a in and solve for y. So I'm going to have 3a plus 2y equals 12. And now I'm supposed to solve for y. So subtract 3a. And I'm going to have 2y equals minus 3a plus 12, because that's equals a positive 12. And then I'm going to divide by 2. And so look what I get. Minus 3/2 a plus 6. Ta-da! All right, so it doesn't matter which equation you use. Whenever you get a number equals itself, you know that's an infinite number of solutions. We're not going to say infinite number of solutions this year. Instead, we're going to write a parametric solution. Okay. All right. So, there is a way to solve these systems by graphing. If I've got 3x plus 2y equals 12, and I have y equals negative 3/2 x, I could graph each of these linear equations. This one, because there's no y-intercept, there's no b value, I just know that I'm going down 3 and over 2. So I have a line like that. Negative 3/2 x is that equation. But what about graphing from standard form? Well, in standard form, I prefer to graph using x and y intercepts. It's really easy to plug in a 0 for x and say, oh look, 2y equals 12, so y must be 6. Or to plug in a 0 for y and say, oh look, 3x equals 12, so x equals 4. And so then I end up here with 0, 6 and 4, 0. And I'm able to see that these lines are parallel. So here's the thing. Sometimes these are really easy to graph, and it's hard to visualize the point of intersection. Sometimes the point of intersection is really easy to find, but graphing the lines is terribly hard. So I would say that I don't use graphing by hand as a way to solve these. I usually use graphing by hand as a way to sort of ballpark how many solutions do I have and where might I find them. Especially in the age of magic box, really, I'll just do second calculate intersect here. Okay, so how about we practice parametric a little more, and then I'd like to move away from sort of linear systems, and I'd like to look at a bunch of non-linear systems. Ooh, and it looks like there maybe are some word problems we could look at. So let's get going. How about 2x plus 3y equals 6 and negative 4x minus 6y equals negative 12. Now, I want to say I've already told you this is parametric, which means you already know that when you're done, you're going to get a number equals itself. It's just that simple. So rather than go to that place, I want to say, okay, so now that I know this is parametric, what am I supposed to do again? Instead of writing infinite solutions, I'm supposed to say, step 1, x equals a. Step 2, plug this into either equation and solve for y. So if I take x equals a and plug in here, I have 2a plus 3y equals 6. I'm solving for y now, so I'm going to subtract 2a from both sides, and then finally divide by 3. And so I'm going to have y equals negative 2/3 a plus 6. Nice. Now I'm almost done, but not quite yet. A comma negative 2/3 a plus 6. Okay, I've got to write that parametric solution in the form of an ordered pair. So if anyone were to come up to us and say, hey, what's the solution to this? You could just plug in a 0 or a 1 or a negative 5 or a positive 6.2 into these A's, and you'd be generating a solution. Now, while I was writing up that parametric solution, I'm really comfortable knowing that this is infinite solutions, but you may not be. So with elimination, if I multiply this top row by 2, I'm going to have 4x plus 6y equals, don't forget 2 times that, 12. And then here I have negative 4x minus 6y equals negative 12. And because these coefficients are opposites, I'm going to add 4 minus 4, 6 plus negative 6, 12 plus negative 12, then I get a big old 0 equals 0. This is how I know that I need to write a parametric solution. Whenever I get a number equals itself, that's parametric. You used to say infinite number of solutions. Now you say parametric solution. And remember, if you get a number equal to a different number, that's going to be no solution. The one we were just looking at, the one for parametric, is you get a number equals itself. And that's parametric. Parentheses, old school, infinite. All right, good. I've never seen a parametric solution show up on ACT or SAT. So I'm not sure how much you have to worry about a parametric solution, but yeah, now you know how to write one. Okay, so let's take a look at some nonlinear things, like y equals x squared plus 1 and x plus y equals 3. So, yeah, I mean, let's just think about this graphically. This is a parabola. It's a parabola shifted up 1. This is a linear equation. You know, if I move that x over, it's going to be y equals negative x plus 3. So I have a linear equation with a negative slope and a positive y-intercept. How many solutions do you expect here? I think it's really good with these systems problems to try and pre-think the number of solutions to help you realize whether or not the answer that you get is reasonable. So here, when I think about a parabola that's been shifted up 1, and that's 0, 1, and I think about, ooh, this has a y-intercept of 3, so that would be up here, and a slope of negative 1, and so I have positive 3, 0 here. And from my very quick graph, from just thinking about it briefly, I know I'm going to have 2 points of intersection. One of them has a positive x, one of them has a negative x. Both of them have positive y values. All that information is helping me to understand when I get my solutions, whether I have the right number of solutions and whether those solutions are in a reasonable place. Okay, so I thought about doing this with substitution. I know what y is equal to, so I'm going to take all this stuff and plug it in for y. So x plus x squared plus 1 equals 3. And yes, I do like writing these in descending order, but I also see that quadratic, which means everything has to come over. X squared plus x minus 2 equals 0. And yes, this will factor as x plus 2, x minus 1. And so I get x equals 1, and I get x equals negative 2. And that makes sense here. I have a positive x and a negative x. Okay, but I'm not done, because the points of intersection have to be ordered pairs. The solution to this system has to be ordered pairs. So I've got half of 2 different ordered pairs right now. So if I take that 1 and plug it in for x, 1 squared plus 1 is 2y equals 2. Likewise, if I plugged in my 1 here and subtracted 1 from both sides, I'd still get y equals 2. Again, don't write your answer that way. Instead, I want to see that way. I want to see that you're thinking about this stuff graphically, not just algebraically. If I plug a negative 2 in for x, negative 2 times negative 2 is 4, plus 1 is 5. And so my second ordered pair is negative 2, 5. And that's how I use substitution there. So yeah, we're going to be doing a bunch of nonlinear systems. So how about you do this one? 2y equals x squared, y equals 4x to the third. Please solve that system. Hey, welcome back. So what I'm wondering is, did anyone use elimination here? I'm going to go back and do it with substitution, but you know, I was looking at this 2y and this y, and I could imagine that there were a bunch of people out there who were saying, well, I'm just going to multiply this second row, or this row by 2. And so they have 2y equals x squared, and then 2y equals, remember, 2 times 4 is 8x to the third. And since the coefficients are the same, I need to subtract, and that gives me 0 equals x squared minus 8x to the third. Some people, of course, like writing that as negative 8x to the third plus x squared. But mostly, I want to get to the factoring part, where I factor out a negative x squared, leaving me 8x minus 1. And so I get x equals 0, and x equals 1/8. And so if I take this 0, plug it in there, 2y equals 0, so y must be 0. So we're passing through the origin. And then over here, if I take my 1/8 and plug that 1/8 in there, 1/8 times 1/8 is 1/64. So 2y equals 1 over 64. But I still have to divide everywhere by 2. And so I'm going to get y equals 1 over 128. So 1/8, comma, 1 over 128. Ta-da! There we go. Yeah, so you can use elimination here, but I suspect most people did substitution. So let's see what this looks like with substitution. Does it look the same? I know what y equals, so I'm going to replace y with what y equals. I have 2, 4x to the third equals x squared. And yes, that's 8x to the third equals x squared. Remember, though, I'm not going to divide both sides by x squared, because when I do that, I'm throwing away the solution x equals 0. I really don't want to throw solutions away. Instead, move everything onto one side of the equation. X to the third minus x squared equals 0. And here we are back in that factoring place. I'm going to factor out an x squared and have 8x minus 1. And I get those same x values, x equals 0 and x equals 1/8. Remember, if I divided both sides here by x squared, I'd be throwing away the solution. So try not to divide like that. Move everything onto one side when you have polynomials bigger than degree 1. Okay? If you're bigger, sorry about that. If you're bigger than degree 1, then yes, you want to move everything over. Okay, a couple more of those. How about this one? This one's great. Y squared equals x, and then x plus 2y minus 3 equals 0. Okay? Now, before you start the solving stuff, let's do a little thinking thing. This is linear, and I can see it in standard form if I move the 3 over. This, it's not y equals x squared, which looks like that. It's x equals y squared, which looks like this. So we're asking about when 3/2, 3, when this linear equation intersects this parabola which seems to have fallen over on its side. And I can see there are going to be 2 points of intersection here. All right, well, go find those 2 points of intersection. One with a positive y and one with a negative y. Okay, so, I always look at this and say, that's so close to the equation of the line the way I expected, but why the hell is this here? Why didn't they leave it over there? And the answer is because they're doing substitution, right? So I'm going to replace x with y squared. And when I do, this is already everything on one side set up for me to factor. Talk about thoughtful textbook writers. That was so nice of them to say, well, what can we do to make it a little easier for them? So I get y equals -3 and y equals +1. And that's fabulous because when I did the quick graph of it, I realized that I'm going to have 2 solutions, one with a positive y and one with a negative y. If I take these y values and plug them in, I'll be able to get x values. So 1 squared is 1, x equals 1. So we have the ordered pair 1, 1. And if I plug a -3 in there, -3 times -3 is 9. And so 9, -3 is my other point of intersection. Okay. I hope you're doing well with these. If you have questions, don't forget to reach out to me. Hey, do you remember what this is? X squared plus y squared equals 25, and x plus 3y equals 5. What's that? I know this is linear, but what's that? We did that a while ago. We did that at the very beginning of our functions unit, and we said that isn't a function. But what is it? Like, that's that sideways parabola. That's that regular parabola, but what's that? Yes, It's a circle. Very good. That's our equation of the circle. Remember, the equation of the circle was x minus h squared plus y minus k squared equals r squared. And so here I see hk, the center of the circle, must be 0 because there's nothing in those places. And over here, r squared is 25, so the radius must be 5. So when I'm thinking about this, I'm thinking about a linear equation, and I'm thinking about a circle whose radius is 5 that passes through, whose center is the origin. So 5, 0, and 0, 5. This line, if I plug a 0 in for y, I get x equals 5. Ooh, I've already found a solution. 5, 0 is where the circle exists, but this linear equation also passes through. If I plug a 0 in for x, I get 3y equals 5 or y equals 5/3. Since this y value is 5, 5/3 would be down here. And so there's my line. Now, I see that there's a second solution. How do I find this second solution? Well, luckily, we know about substitution and elimination. I don't think I want to go anywhere near elimination here because I have to square both sides of the equation. Not square this, and square this. That's pool noodle. Don't ever do that. But instead, square the whole side. And that's going to bring in extra xy terms. I really don't want to see that movie. Instead, I'm just going to solve this equation either for x or y. I like x too, because if I solve for y, I'm going to end up with fractiony stuff. I really don't want to put fractiony stuff in there. So I'm going to say x equals 5 minus 3y. I'm going to take that and plug it in there. 5 minus 3y squared plus y squared is 25. Don't forget to FOIL here. This is 5 minus 3y times 5 minus 3y, not simply applying that exponent to both of these. So you should end up with 25 minus 30y plus 9y squared plus y squared is 25. Well, I can subtract 25 from both sides, and I can combine these like terms. So now I'm going to have 10y squared minus 30y equals 0. And if I factor out a 10y, I have y minus 3. And wait a minute, I thought they intersected at 5. And 5, 0. Yes, okay. Sorry, I thought these were x's for a moment. So what happens now is I set each of these equal to 0 and get y equals 0 and y equals 3. But I need the ordered pairs. So if I plug in y equals 0 here, I get x equals 5. So I know one solution is 5, 0. And I know y equals 3. If I plug a 3 in here, 3 times 3 is 9. X plus 9 equals 5. I need to subtract 9 from both sides. And so 5 minus 9 is negative 4. Negative 4, 3 is my second solution. Okay? All right. One more. How about two parabolas? Y equals 2x squared plus 4x minus 5. And y equals x squared plus 6x minus 2. Okay, we've got two up-pointing parabolas, and we wonder, well, how many solutions am I getting? There's lots of different ways for me to have two parabolas. I could certainly have two parabolas that never intersect. I could have two parabolas that intersect twice. Can I get them to intersect once? Yeah, I could do something like this and something like this. And so I only get that one point of intersection. So none, 1, or 2 is the number of solutions I expect here. But how am I going to find them? And so I think this is a case where I don't want to do substitution. I mean, I can do substitution. Look, I know what y is equal to. So I'm going to take all this stuff and shove it over there. X squared plus 6x minus 2 then equals 2x squared plus 4x minus 5. And so I'm going to subtract x squared, and I'm going to subtract 6x, and I'm going to add 2. And so I end up with 0 equals x squared minus 2x minus 3. And certainly that will factor as x minus 3 and x plus 1. I know the x coordinates of the points of intersection, but I still need to find out what y equals. So I'm going to say I better plug in, oops, negative 1. I better plug a negative 1 in for all the x's in one of the equations. Negative 1 squared is 1. Negative 1 times 6 is negative 6. 1 plus negative 6 is negative 5. Negative 5 minus 2 is negative 7. And if I plug in a 3, 3 squared is 9. 6 times 3 is 18. 9 plus 18 is 27. Minus 2 is 25. And so there are my two solutions. Okie doke. Oh, but I was actually going to say, what if we did elimination here? So yes, I can do substitution because one of the equations is already solved for one of the variables, and so I just take all this stuff and plug it in there. But with elimination, y minus y is 0. 2x squared minus 1x squared is x squared. 4x minus 6x is negative 2x, and minus 5 minus a minus 2 is minus 3. And look, it's all set up and ready for me. And so, substitution is good, but I like elimination when I can use it. Okay, so the last thing I want to do is I want to look at a couple of word problems, and let's talk about lemonade stand. An American trope is that the kids will go out in front of the house and sell lemonade to the passersby and generate the money that they need to do the thing that they want to be able to do or buy. And, in a place like Tucson where most people don't walk but drive, lemonade stand is a much harder business. Also, kids are maybe more worldly and wise. And maybe staying with the model of one stand won't be enough for them. So, lemonade stand. It costs you $18 to get a table, a sign, little tablecloth. How about some lemonade that you made? 18 bucks. But then you realize that to make the cups of lemonade, you're gonna have to, have these additional costs. Like every time they take one, you've lost a cup. So you need to pay for the cups, you need to pay for the lemonade, and you figure out that the variable costs are going to be 10 cents for each cup of lemonade you sell. Okay? And so this is my cost equation. Now, revenue, what you bring in, the money that comes in, you're going to sell this lemonade for $1 a cup. And so your revenue is going to be $1 for each cup. Or you could just write 1C. Now, the first thing I want to know is, how many cups of lemonade do you have to sell before you break even? And break even means that your costs equal your revenue. All right, so cost equation equals revenue equation. 18 plus 0.1C should equal C. Because these are to the first, I'm going to subtract 0.1C from both sides. So I'm going to have 18 equals 1C minus 0.1C, or $1C minus 10 cents C, is 9.9C, or 90 cents times the number of cups. All right, well, let's divide both sides by 0.9. Now, for those of you who are wicked lazy like me, 0.9 is the same as dividing by 9/10, so I can flip and multiply, and that's going to be 18 times 10 over 9. Those cancel, giving me 2. 2 times 10 is 20. So if I sell 20 cups of lemonade, I will break even. I will have paid all my costs. So if I want to make a profit, if I want to have some spending money after this, I have to sell more than 20. Okay? All right. So, yeah. Let's imagine the situation where you decide that you need to upsize your business, your lemonade stand business. And so now that you upsize it, the cost, the fixed cost, is $29,800. You're still going to be selling, I'm sorry, it still costs you 10 cents per cup for lemonade. But dude, you bought a bunch of machines. It's all in a factory now. And so you had a lot of upfront costs. Hired some minions to work. Revenue, though, you're going to charge more because tell everyone you have a better product because you hired some marketing people in this money. So your revenue now is going to be $1.50 per cup. So can you first create the system, and then let's ask the question, how many cups do you need to sell in order to break even? Okay. I was worried about that because some people really still get stuck with, well, I don't know how to make this information into an equation. I mean, we may have done it on the third day of school, Mr. Cooper, but yeah, I don't remember. And so what I've been saying since Algebra 1 is rate of change times the variable plus the initial amount. That's my recipe for linear models. And because these are constant slopes, I know I'm writing linear equations here. My cost function should be rate of change times the variable plus the initial amount, or plus my fixed cost. Variable cost plus fixed cost. This is called a variable cost because this amount depends on how many cups I sell. This is even if I sell no cups, even if I make no cups, I still have now spent all this money, part of my costs. My revenue, on the other hand, $1.50 for each cup, 1.5 for each cup. So now I've got these two linear equations, and I want to know my break-even point. I want to know when my costs equal my revenue, when R equals cost. So I'm going to say, sure, let's just do this. Set those two equations equal to each other. Subtract so that you have 29,800 equals 1.4C. And I need to divide both sides by 1.4. 1.4 is 14 over 10. So that's going to be 7 over 5. And if I do the flip and multiply thing, it's 5 over 7. Yeah, 7 into that. Yeah, no, I'm not going to do that. I'm just going to pull out the damn calculator. See, I'm lazy, but there's only so lazy. Okay, 29,800 divided by 1.4. And I get that I'm supposed to sell, is that really 29,800? Yes. 1.4, yes. I need to sell 21,285.714 cups. All right, we're thinking big here. Um, yeah, and that's just a break even. It's not until we make 2, 1, 2, 8, 6, or sell that many, uh, that we end up making a tiny, tiny profit. Okay, the last thing I want to remind you about uh, is interest. Not the interest from exponential growth problems, but simple interest. Simple interest. You actually learned about simple interest in middle school, where interest was equal to um, rate times time times principal. And what that means is, if you've got $100 and you put it in the bank and the bank gives you 2% interest and you leave it there for 10 years, then you're going to have $20 worth of interest. Okay, it's just a matter of multiplying principal times the rate times the time. Fabulous. This is simple interest. Now, I will say that in all our systems word problems where we see interest showing up, time is 1 year. So our interest equation is just going to be rate times principal. Okay? All right. With that in mind, let's now say, hey, you've got money. Grandma says you're going to college, and you want to invest this money wisely. So you put some of it into one investment and some of it into another investment. Why two different investments? Well, to sort of hedge your bets. If this one completely tanks, you didn't lose all your money. If this one completely tanks, you didn't lose all your money. So I would say, yeah, that makes sense. Now, it's known that the amount of money that you invested in this A account earns interest at 2% for A and 2.5% for B. Now, clearly, if you invested all your money just in B, you'd make a little more interest. But because the world doesn't come with guarantees like that, you decide to spread your money up across these two investments. So how do we turn this into an equation? Well, we need one more piece of information, and that is that the interest that you earn from 1 year of these investments is $105. Okay? All right. So what was that simple interest formula? It was principal times rate. This is how much money, right? A plus B should add up to 5,000. This number is between 0 and 5,000. This number is between 0 and 5,000. This is the amount of money. Yeah, it's the amount of money that we want to then multiply by the interest rate. So I'm going to say 0.02A plus 0.025B equals 105. 2.5%, right? Because that's 2% and then half of one more, going to the third decimal place. So now I've got my two equations and two unknowns. I've got my quantity equation and my value equation. So 0.02A plus 0.025B equals 105. And what do you want to use? Do you want to use elimination? Do you want to use substitution? Myself, I would probably use elimination and multiply this row by 0.02 so that these could be the same. But, a lot of students aren't actually comfortable doing that and would prefer to solve one of the equations for one of the variables. So I can say that A equals 5,000 minus B, and I can plug that in there. Okay, so I'm going to have 105 equals 0.02, 5,000 minus B plus 0.025B. I do have to distribute. 0.05 equals 2%. It's 2 over 100. So 2 over 100 times 5,000. Cancel, cancel. 2 times 50 is 100 minus 0.02b plus 0.025b. If I add these together, I get 0.005b equals, and if I subtract 100, 5. So to get b by itself, I have to divide both sides by 0.005. So 5 divided by 0.005. And I get 1,000. If b equals 1,000, and I invested a total of 5,000, a must be 4,000. Okay. Any questions? Okay. Well, here's one for you. Modeled on the same. Well, this will be our last problem. Modeled on the same, you've got 2 investments. Or you want to spread this money you have into 2 investments. How much money? You've got a total of $10,000. And one of the accounts gets 3% interest, and the other account gets 2.5% interest. The total interest for the year should be $263.75. Okay, so first write the system, and then come back. Just want to make sure everyone's got the right system here. So I've got A plus B equals 10,000. That's my quantity equation. Now my value equation, 0.03A plus 0.025B equals 263.75. So there's my system. And of course, you could have these flipped, and that won't matter. Now, go solve it. So, what method did you use? Decimally scared. Do you want to use substitution? Do you want to use elimination? We should definitely use one of those. We should definitely use one of those. I think last time we did the substitution, so I think this time I'm going to multiply everywhere by 0.03 in this first equation. 0.03. That's 3 over 100. So those go times 3, I get 3. Okay. And now I can do my elimination. Since these coefficients are the same, I'll subtract. 0.03b minus 0.025b is 0.005b. And here 300 minus 263.75 is going to be 36.25. Yeah? So now I need to divide by 0.005. And so in this situation, I find out that b is equal to 36.25 divided by 0.005, and I get 7,250, which means if the total amount invested was 10,000, I have 2,750 to invest at 3%. 2,750 at 3%, and 7,250 at 2.5%. There you go. Welcome to Systems. I'll see you in the next video.